Hello, and welcome to our webinar. I'm Ken Loudermilk, Senior Chief Engineer for Titus. Over the next 45 minutes or so, we'll be discussing displacement ventilation as it applies to K-12 classrooms. We'll also explore the combination of displacement and air-water technologies to optimize the performance of these systems. At the end of the presentation, we will welcome any questions you might have and will attempt to answer them. So feel free to submit those questions at any time during the broadcast. Today we will discuss the role of HVAC in the classroom acoustical requirements and how they were developed, and talk about displacement ventilation solutions for the classroom, HVAC, and discover how chill beam technology can be combined with displacement ventilation to optimize the classroom environment while reducing energy and maintenance costs. The HVAC system's performance has a huge impact on K-12 schools. The maintenance of a comfortable and healthy learning environment has proven to improve both student performance as well as teacher retention. Proper classroom ventilation not only keeps the students alert, but also has a significant effect on respiratory disease transmission. Excessive background noise created by HVAC equipment can compromise the student's ability to hear and understand the teacher, especially in lower elementary levels. This too often also leads to teacher vocal stress, absenteeism, and poor student performance. Classroom acoustical design should ensure that all of the students can hear and comprehend the teacher's voice spoken at normal, comfortable levels. According to the Acoustical Society of America, most teachers speak comfortably at a sound level between 50 and 60 dBA. As the teacher's voice is transmitted to the students, background noise from sources within and outside the classroom, as well as reflection between surfaces within the classroom, interfere with the student's ability to comprehend the message. One of the foremost sources of background noise is the HVAC system. In order for the teacher's message to be adequately heard and understood by the students, it should be at least 15 dBA above the background noise level. Therefore, the background noise level should not exceed 35 dBA. Here are some statistics regarding the impact of classroom acoustics. Some 13 to 15% of K-12 students suffer from slight hearing impairment. Now, this may include a simple ear infection that is temporary as well. In addition, 10 to 15% of K-12 students are learning in a language that is not spoken at home, and this is growing every day. Now let's look at the cost of poor classroom acoustics. 3% of students have hearing impairments that require out-of-class support services. The cost of these services average some $2,500 per year. Another 1% suffer from impairment so severe that they require outside placement into environments specially tailored for the hearing impaired, the cost of which averages around $15,000 a year. All this adds up to annual cost of about $6,300 or $7 per square foot per classroom. In 2002, ANSI developed a new standard for classroom noise levels. The standard's objective is to assure that all students, even those with slight hearing impairments, are able to hear and understand the teacher. It is aimed at increasing student performance and reducing teacher vocal stress. The standard calls for a background noise level that does not exceed 35 dBA. This equates to a sound pressure level of NC 27 in all of the core learning areas. This has a significant impact on HVAC equipment selection and placement in and in the proximity of the classroom. The standard also limits the reverberation times within the classroom to 0.6 seconds or less. This slide illustrates the state of affairs shortly after this standard was published. In 2005, the AHRI commissioned a design firm which specializes in K-12 education to perform acoustical testing in Minneapolis classrooms in order to determine their background noise levels when students were not present. 48 classrooms were tested during the survey. Almost half of the classrooms tested in this study had background noise levels above 50 dBA, which converts to an NC of about 42 when the HVAC systems were operating. Unfortunately, none of the 48 rooms measured would have complied with standard S1260. These are some of the HVAC systems that are commonly used in K-12 applications. All of these would require costly modifications to comply with the ANSI S1260 recommendations. Some, such as unit ventilators and vertical fan coil units, would likely never be able to comply. All of these systems are also what we refer to as a mixed air system. Let's talk about mixed air systems as we go forward. Almost all HVAC systems used in North America today are mixed air systems. Let's quickly review the design basics and operational characteristics of these systems. Mixed air systems introduce conditioned air at 55 to 57 degrees through diffusers that are commonly ceiling mounted. These diffusers usually discharge the air horizontally across the ceiling, attempting to make use of a capillary effect of the ceiling surface, which is referred to as the Coanda effect. An adequate discharge velocity is maintained to induce room air and mix it with the cold conditioned air such that the velocity and the temperature differentials are dissipated before the supply air stream enters the occupied levels of the space. The objective of a mixed system is to create a perfectly homogeneous mixture of air throughout the space. If successful, the following will occur. The temperature at any location within the space is relatively constant. There are no vertical temperature gradients that are obvious when the air is fully mixed in the space. Unfortunately, gaseous contaminants are also equally distributed. This includes the germs that come from the occupant's respiration within the space. Heat gains from sources located throughout the room are transferred to the occupied levels and must be included in the room's sensible cooling calculations. This includes lighting and high-level heat gains that occur along the perimeter of the space. This type of ventilation is referred to as dilution ventilation, as it uses the fresh air supply to dilute the room air, thereby reducing its contaminant level. It should be noted that over 60% of contagious disease transmission in K-12 schools is due to respiratory exchange. This figure relates the temperature relationships for a fully mixed system. Note that there is little or no difference between the floor and ceiling level, and that both temperatures are very nearly the same as that at the control level of the space. As such, the airflow required to provide sensible cooling to that space can be calculated by this equation. Also note that the airflow requirement is inversely proportional to the temperature difference between the supply air entering the space and the return air leaving it. We generally consider this delta T to be that between the supply and room air. In the case of mixed air systems, that generally works because the return air temperature is very close to that of the room. This figure relates to the concentration of CO2 in a mixed air system. The term zone ventilation effectiveness relates to the concentration of gaseous contaminants in the return air leaving the room to that at the occupant breathing level. Note that the CO2 concentration in the return air leaving the classroom will always be equal to or less than that at the breathing level of the room. Thermal displacement conditioning systems typically utilize low sidewall or floor level supply outlets. These outlets discharge conditioned air at a very low velocity and a higher temperature than overhead mixing systems. Since the conditioned air is cooler than that within the room, it falls immediately and spreads evenly throughout, creating a thin layer of conditioned air along the floor surface. The presence of warmer ambient air above this layer prevents it from rising through the room to the return outlet located at the ceiling or high sidewall location. When students enter the room, they are warmer than the room air, so they transfer heat to the environment surrounding them. This transfer of heat creates a convective plume around the students' bodies. Cool conditioned air is induced from the reservoir near the floor to replace the air induced by the heat plume. It conditions the students and serves as a source for their inhaled respiration. When the students exhale, that air is warmer than the ambient air, thus it escapes upward with the heat plume, carrying its respiratory contaminants with it. Heat gains such as those from lights that originate above the conditioned air reservoir escape naturally and do not affect the amount of air required to condition the occupants of the space. This figure relates the temperature relationships for a thermal displacement system. Note the temperature gradients between the ankle and the return air levels. This gradient forms as a result of space heat gains that occur above the supply air layer. The airflow required to provide sensible cooling to the space can be calculated by the same equation used for mixed air systems. In the case of a classroom with a conventional 9-foot, 10-foot ceiling height, the differential between the supply and return air temperatures is around 17 to 18 degrees Fahrenheit, meaning the displacement system airflow will be some 15 to 18% higher than that required with a mixed air system. This figure relates the concentration of CO2 in a displacement system. Note that the concentration gradient essentially begins at the breathing level, and the return air concentration is sizably greater than that within the occupied zone. With thermal displacement, the CO2 level in the return air will always be greater than that at the occupant's breathing level. Although the supply air temperature for displacement systems is higher than for mixed air systems, the low velocity discharge results in less mixing with the ambient air. This and the fact that the diffuser discharge is directly into the occupied zone results in areas adjacent to the outlet where occupants may feel some discomfort. This area is defined as the adjacent zone, and location of stationary occupants within the area is generally discouraged. The plan view on the right depicts the adjacent zone of a sidewall outlet discharging into a classroom. It is advisable that the adjacent zone links be minimized in order to reduce the occupant discomfort potential and therefore maximize the usable classroom space. Although displacement ventilation as a method of air conditioning was pioneered in Northern Europe and the Scandinavian countries, they weren't exactly the first to apply its concepts. Our Native Americans relied on the same thermal stack effect to ventilate their teepees. Displacement diffusers come in a variety of types. They can be flush-mounted in the sidewall, such as Titus's DVR1 and DVIR models. They can also be mounted along the sidewall, such as these Titus models. Finally, they can be corner-mounted, such as the Titus DVCC and DVC1 models shown here. Corner mounting across the classroom from the windows is very common for K-12 applications. Titus displacement diffusers utilize modular pattern control elements that allow the distribution of discharge air to be redirected to suit the application. For example, the adjacent zone of the sidewall mounted diffuser can be modified to increase the amount of classroom occupied space by spreading the air more along the wall and having less of a vertical intrusion into the classroom itself. The application of displacement ventilation in classrooms has a number of advantages over mixed air systems. Classroom noise levels compliant with ANSI standard 1260 are easily obtainable due to the reduced discharge velocities and static pressures involved in the displacement systems. The higher supply air temperatures used in displacement systems may also extend the range of economizer cycles when these systems are applied in mild or moderate climates. And finally, contaminant removal efficiencies with displacement are significantly greater than those achievable with mixed air systems. Recognizing this, ASHRAE Standard 62.1, Ventilation for Acceptable Air Quality, awards a zone ventilation effectiveness factor of 1.2 to thermal displacement systems as opposed to only 1.0 for the ceiling supply of cool air with ceiling return. This essentially means that a displacement ventilation system can deliver a similar contaminant removal efficiency as a mixed air system, while that is delivering 20% more outside air to the classroom. Proper zone temperature control is critical to achieving this enhanced level of contaminant removal. In order to satisfy space cooling demand, the supply air volume flow rate and/or temperature has to be varied. One commonly used method involves the use of series fan terminal units. Conventional 55-degree supply air is delivered to a series fan terminal and then mixed with return air from the ceiling plenum to establish a constant volume, variable temperature delivery of air to the space. This is, however, not advisable, as recirculation of return air will just short-circuit the contaminants back into the space itself. A better air quality alternative is to employ a constant temperature variable volume solution. Supply air is delivered at the intended discharge temperature to a single duct terminal, which then throttles the airflow rate to meet the zone cooling demand, establishing a variable air volume, constant temperature delivery of air to the space. It should be noted that the airflow should only be reduced to a level that still assures that acceptable space humidity levels are maintained. This may necessitate the use of reheat when the zone temperature demand drops below the cooling delivered by the supply air at that reduced airflow rate. Despite these significant advantages, applying displacement systems also pose certain challenges to the designer. As previously mentioned, the higher supply air temperature employed by displacement systems results in a slightly lower delta T between the supply and return air when the systems are used with conventional 9 to 10 foot ceiling heights. This commonly results in supply air volume flow rates for sensible cooling that are some 15 to 20% greater than that would be required by mixed air systems. In addition, displacement systems often require a separate decoupled heating system. Low-level fin tube heating is typically supplied along the outside wall of the classroom. Again, referring to ASHRAE Standard 62.1, systems which involve the floor supply and ceiling return of warm air are awarded a ventilation effectiveness of 0.7, resulting in a significantly higher outdoor air delivery during heating operation. Titus offers a version of our DVRI diffuser that is designed to provide both heating and cooling to the classroom. The units have separate supply plenums for the hot and cold air. When the terminal is in cooling mode, a temperature sensing probe positions an internal damper to supply the air into the upper section of the diffuser. The air then discharges into the classroom in a displacement manner. During heating mode, the supply air is diverted to the smaller, lower section of the terminal and discharged with a greater velocity to increase its penetration into the space and provide more mixing with the classroom air. The Plexagon version of this terminal features light harvesting elements which provide power to the actuator to accomplish the changeover. This version requires no outside power connections and works strictly off the ambient light in the classroom itself. Perhaps the biggest challenge for displacement system application in moderate to humid climates is maintaining adequate dehumidification within the classroom. A displacement system serving a classroom must typically provide supply air at 63 to 65 degrees Fahrenheit to satisfy the sensible cooling load and a humidity ratio of 57 grains to maintain the desired classroom humidity level. Outside air is mixed with return air within the air handling unit before entering the cooling and dehumidifying coil. When applied in humid climates, the condition of this entering air at design conditions is typically about 80 degrees Fahrenheit with a humidity ratio of 80 to 85 grains. Simply conditioning the air mixture to the desired delivery temperature would not adequately dehumidify the supply air stream and would result in excessive classroom humidity levels, especially during off-peak cooling operation. In order to adequately dehumidify the supply air, the outside recirculated air mixture must be conditioned to saturation at about 54 degrees Fahrenheit, then reheated to its desired delivery temperature. Depending on how it's accomplished, this reheat requirement can significantly increase the energy use of the HVAC system. This slide illustrates a common configuration of an air handler used with a displacement system. Outside air and return air enter the air handling unit. Some of the return air is mixed with the outside air to make up the supply air volume to the space. This mixture then passes through the cooling and dehumidifying coil and is cooled to saturation to obtain the required supply air humidity ratio. It is then reheated to bring it to the desired discharge temperature before delivery into the classroom. An effective way of providing the necessary reheat is to provide a heat pipe or runaround coil to transfer heat from the air mixture before it is cooled and dehumidified to reheat the air leaving the coil. Titus also offers the displacement terminal that combines all of the aforementioned displacement advantages with energy-efficient chill beam technology. TOW displacement chill beams mount beneath the windows along the exterior of the classroom and are an ideal solution for new school construction, as well as a replacement for noisy HVAC equipment such as unit ventilators and fan coils. This slide illustrates an installation of TOW displacement chill beams in a K-12 classroom. The TOW is an active chill beam that maintains a displacement flow to the classroom during both cooling and heating mode. TOW terminals are provided with separate internal cooling and heating coils. As with all active beams, the cooling coil is supplied with chill water whose supply temperature is above the room dew point to avoid condensation formation on the coil surfaces. As the cooling coil is vertical, a condensate tray is provided to catch any moisture that might form during periods when the room dew point exceeds the supply water temperature. The unit also consists of a ducted primary air plenum, several rows of nozzles which inject the plenum air into two separate induction sections, and separate mixing sections where induced air, room air, mixes with the primary air injected by the nozzles before being discharged to the classroom. During cooling mode, preconditioned primary air at 55 degrees is delivered to the unit by the air handling unit. This air pressurizes the primary air chamber and is discharged by several rows of induction nozzles into the upper and lower mixing plenums. Mechanical energy created by the nozzles draws room air through both the cooling and heating coils. During cooling mode, chilled water is circulated through the cooling coil. Sensible heat is removed from the room air that is drawn through the cooling coil. Water flow to the upper heating coil remains off during cooling mode. The reconditioned air mixture mixes with the primary air and is discharged in a low-velocity displacement manner to the classroom. Primary air injected into the upper part of the unit mixes with room air and is then discharged to the space slightly cooler than the room itself. 85% of the primary air is discharged through the lower mixing plenum, while the remaining 15% is discharged from the upper portion of the terminal. During heating mode, primary air is delivered at a slightly higher temperature, but still some 10 degrees below the classroom control temperature. This air pressurizes the primary air chamber and is again discharged by several rows of induction nozzles into both the upper and lower mixing plenums. Nozzles feeding each chamber draw room air through both coils. Although there is no flow of chilled water through the lower coil, the fact that the primary air temperature is depressed results in a discharge temperature that is still slightly lower than that of the room. Water flow to the upper heating coil warms the air induced into the upper portion of the unit. As its temperature is still slightly lower than the room, the primary room air mixture from the lower mixing plenum still discharges in a low-velocity displacement manner. The mixture of heated room air and primary air in the upper section is discharged vertically up the outer wall. The heating coil within the TOW units can supply limited, unoccupied heating even when the air handling unit remains off. This slide illustrates a classroom fitted with TOW terminals. Primary air and the chilled and hot water supply is delivered through the ceiling cavity of the classroom. These services then drop through either chases provided by others or duct covers furnished by Titus and mounted in the two corners of the classroom adjacent to its outside exposure. The water supply for all of the TOW units can be provided through one chase and returned through the other. The individual TOW heat transfer coils are fed in parallel, and the piping is run behind the units and against the wall. Primary air is supplied to multiple TOW units in series. A single duct connection should be limited to feeding no more than 3 units due to noise and pressure limitations. So often this involves air supply connections on both sides of the classroom. Spaces between the terminals can be filled with custom filler sections that match the appearance of the TOW units, or may be filled with bookcase sections. For applications with high nighttime heating requirements, a static heating terminal can also be used to fill the space between the terminals. This slide applies the typical classroom cooling and occupancy loads to the conventional all-air displacement system we discussed earlier. It's based on a 750 square foot classroom whose maximum occupancy is 30 people. Note that most classrooms have relatively low sensible heat gain ratios, as is the case in this example. The delivery of 63-degree supply air at a humidity ratio of 57 grains will allow us to handle both the latent and sensible cooling loads of the classroom at the same supply airflow rate, in this case 1100 CFM. The air handling unit shown is classified as a mixing type air handling unit. The outdoor airflow rate of 15 CFM per person demands that a minimum of 450 CFM of outdoor air be delivered to the classroom at all times. Therefore, 650 CFM of return air will be mixed with the outdoor air to constitute our 1100 CFM supply airflow delivery to the classroom. This mixture will then be cooled to saturation at about 55 degrees within the cooling dehumidifying coil to reduce its moisture content to the required 57 grain level. This will require about 3.6 tons of cooling. It must then be reheated to its discharge air temperature of 61 degrees using the runaround coil. Its temperature will be assumed to rise by another 2 degrees before it's discharged into the room. The return and exhaust air conditions are also shown on this illustration. This slide illustrates an air handling unit that is commonly used with a displacement chill beam system. Notice that the unit delivers 100% outside air to the classroom. It utilizes energy wheels to transfer heat and moisture between the supply and return air streams, but never mixes the streams themselves. This type of air distribution system is referred to as a dedicated outdoor air system, or a DOWS system. Outdoor air is immediately introduced to a total energy wheel where heat and moisture from the outdoor air is transferred to return air that is then exhausted. The supply air then passes through a passive desiccant wheel where moisture from the air leaves the cooling and dehumidifying coil and is transferred to the outdoor air stream in exchange for sensible heat, which passes to the conditioned supply air stream leaving the coil. In this case, only 2.1 tons of refrigeration is required to condition the air at the cooling and dehumidifying coil. The air is then delivered to the classroom at a slightly higher temperature, but a depressed dew point. It drives the room air induction process through the tau cooling coil, where additional heat is removed from the recirculated room air. This heat is equivalent to about 0.7 tons taken from the room itself. In total, 2.8 tons of refrigeration has been expended compared to 3.6 tons by the conventional all-air displacement system. That's a savings of 23% on the system cooling energy. This slide compares the classroom airflow rate requirements for the two systems. Airflow rates are expressed in CFM per square foot. The outdoor airflow rate indicated by the green bar for the two systems should be basically the same, as it is mandated air supply that passes through the air handling unit. The conventional all-air displacement system requires about 1100 CFM, or about 1.45 CFM per square foot, to satisfy the space sensible load. This is based on a 17-degree delta T between the supply and the return air. Note that the supply airstream has been conditioned to a moisture content that will result in a flow rate for latent cooling that is equal to that required for the sensible cooling. Now, let's look at the displacement chill beam system. The displacement beam system design focuses on providing latent cooling of the classroom at the lowest possible airflow rate, thus the employment of the depressed dew point primary air. In this case, about 0.6 CFM per square foot is required for the space latent cooling. Although the same amount of moisture must be removed from either system, the displacement beam system is able to do so at a much lower airflow rate. The displacement beam system is required to remove the same amount of sensible heat from the classroom, but relies on chill water system to achieve most of the sensible heat removal, in this case about 60%. This results in a supply airflow rate that is similar to that required for the space latent cooling and ventilation, and is some 60% lower than that required by the conventional displacement system. It should be noted that the use of depressed dew point primary air would be of little benefit with the conventional system, as the airflow rate is driven by the sensible and not the latent cooling. Displacement beam systems are often operated with constant volume flow rate of primary air, while the space temperature is maintained by modulating the flow rate of chilled water through the terminal unit's coils. They can also be operated as dual constant volume to reduce the supply of air during unoccupied periods. During normal operation, a constant volume airflow rate is maintained while the water flow rate is dependent on the space temperature demand. Upon a rise in the space temperature, the primary airflow rate is maintained while the chilled water flow is modulated in response to the space cooling demand. An occupancy sensor reduces the primary airflow rate when an unoccupied state is detected. This setback airflow rate should be maintained at a level adequate to deal with anticipated space moisture gains during those unoccupied periods. As a safety measure, float switches can be incorporated into the terminal's condensate trays that will sense the level of condensate and shut off the chill water flow as long as a certain water level is exceeded. Once that water level goes down, then the flow switch will reactivate the chilled water supply to the space. Finally, demand control ventilation can easily be applied to displacement beam systems as well. A controller with temperature, CO2 level, and humidity inputs is employed. When the classroom is fully occupied, a constant volume primary airflow rate and a chill water flow rate sufficient to handle the sensible and latent cooling requirements are maintained. Upon a rise in the classroom temperature, the controller increases the terminal unit's coil's chilled water flow rates. In the event the CO2 level drops, indicating reduced occupancy, the controller reduces the airflow rate of the VAV terminal serving the classroom. This is often accompanied by a reduction in space temperature, to which the controller reduces the chill water flow accordingly. Finally, a rise in the classroom dew point temperature that exceeds the chill water temperature will result in the controller increasing the classroom primary airflow rate to overcome this. Upon restoration of the space dew point temperature, the controller will reduce the primary airflow rate accordingly. You might ask, how do we derive the 56 to 58 degree chilled water required for the terminal unit coils while still maintaining adequate dehumidification within the air handling unit? The higher water supply temperature for the chill beams can be derived in several ways, but this slide illustrates a method commonly used in K-12 school applications. Low temperature chilled water is supplied by a shared chiller and used for cooling and dehumidification in the air handling unit coil. The low temperature chilled water also passes through one circuit in a plate heat exchanger, while return water from the beam loop passes through another separated circuit. A bypass valve adjusts the volume flow rate of beam loop return water passing through the heat exchanger to maintain the desired chilled water supply temperature to the beams. This is a very effective method of maintaining the beam system's chilled water temperature, as it eliminates any possibility of low temperature chill water passing into the beam loop. A DX air handling unit might also be used, enabling the use of a small dedicated chiller to produce the 56 to 58 degree chilled water used by the displacement beam loop. Doing so could increase the chiller operational efficiency by as much as 40%. Finally, many climates may be able to incorporate geothermal fields to utilize groundwater temperatures that are very near those required by the displacement beam loop. This can significantly reduce the facility's cooling energy requirements. This concludes today's presentation. Let's move to some of the questions that we've received during this webinar.